In today's lesson on light and telescopes, we're going to be looking at the three different powers of a telescope. The first of these being the light gathering power, which is the ability of a telescope to collect light. And this is a simple ratio between two different telescopes. The second is the resolving power, which is the ability of a telescope to resolve fine detail in an image. For example, separating of two binary stars. And the third power is the magnifying power of a telescope, which is the ability for a telescope to make an image bigger. Of these three different powers, I've kind of put them in the order I feel that is most important. Light gathering power is probably the most important factor in any telescope. That's the whole point of adding that ability to collect more photons. Without those photons, you don't have an image. The second most important factor is definitely the resolving power. The ability for the telescope to separate two objects is very important when you're trying to create an image or to see detail with your eyes. And third, the magnifying power isn't really as important as you might think, even though this is the one that people most times will cite with a telescope as being an important factor. It's actually not as important as you would think. So the first of these equations is the light gathering power. And with light gathering power, we're going to have the light gathering power of telescope A over telescope B. This side of the equation we can just leave alone. This is the simple ratio as I was discussing before. Where you have to include information is you have to include the diameter of telescope A over the diameter of telescope B, and then we need to square that difference, or square that value. So for these, we just need to make sure that both of these units are identical. So for example, if you gave telescope diameter A in millimeters, then you need to give the telescope B in diameter in millimeters also. If this is in centimeters, this one has to be in centimeters, and so on. So for the next one, the resolving power, we have the resolving power right here is in arc minutes. Remember, there are 60 arc minutes per degree. And I apologize that there's an error here, and I don't know that I'm going to be able to correct it right now. This should really say arc seconds, given the number I'm giving you right here is going to be in arc seconds also. And this on your paper should be 13.8. As you can see, I cannot edit that right now. I apologize. So with this, the resolving power, it should be in arc seconds, is equal to 13.8 over the diameter of the telescope in centimeters. This is, once again, just for optical telescopes. And if we are using a different type of light, then this number up top here would change. So for each one of our example problems, we're going to be working with optical telescopes. And finally, the magnifying power calculation, you're going to solve for M magnification, which is just a multiplier. It's the focal length of the objective lens, or mirror, which is the telescope's main optical device, divided by the focal length of an eyepiece. And this is the part of the telescope that can be exchanged for the purpose of changing that magnification, and as a result, changing your field of view. To do some quick warm-up questions, I'm going to reference you to my key, so just give me a moment. So now that we're looking at the key for the warm-up questions, you might want to pause this video throughout to copy these things down. We're talking about an interferometer. An interferometer is actually 3 or more telescopes that are working in unison to create what is effectively a virtual telescope. So with this, there's two main points that are helpful. You can take the light gathering power of telescope 1 plus the light gathering power of telescope 2 plus the light gathering power of telescope 3, as is shown in this equation, and you can combine them together to get additional light gathering power. But the real power of the interferometer is the ability to resolve an image, because effectively you can take the entire diameter of the distance between the telescopes, or the array, and you can use that as your diameter in the resolving power calculation. So with this, you get a huge benefit of having a virtual telescope that is much, much larger than any of the individual telescopes that make up the array. So an interferometer is an amazing tool that scientists are using in modern times to make very high resolution images of the night sky. Question number 2, once again, the use of and benefit of an interferometer. Most is light gathering power is an additional factor, but the real benefits are seen in resolving power. Active optics are the ability to help to correct problems found in the telescope design. So most times when you build a very large telescope, the mirrors become extra heavy, and there's also expansion and contraction due to temperature change, or movement due to the launch of a telescope into outer space. And as a result, we, in active optics, have the ability to change the actual shape of the mirror after the telescope has been placed at its location to observe. So, for example, if I point at a star on one side of the horizon, and then I slew to the other side of the horizon towards the west, for example, if I start in the east and move towards the west, that will change the way that the mirror itself is sagging, and as a result, we can recorrect the mirror using active optics. Adaptive optics, on the other hand, is to help correct for atmospheric seeing conditions. And so this is the process of using a secondary, what is effectively a fake star that we use a laser beam to create. And with that laser beam, we are making this fake star to monitor its position many times a second. And we use a small bendable mirror to correct for the changes that we're seeing in the atmosphere. And I'll go over this in more detail in class and also in a video that's coming up. Let's get into the actual calculations here. So you're going to be rewriting the formula for light gathering power. And I'll go over the first one here with you. So for our first one, we have the diameter of telescope A is 10 meters. The diameter of telescope B is 0.5 meters. And we're asked to solve for how much more multiplication, magnification power, how many times more light is telescope A getting than telescope B. And so we take 10 meters over 0.5 meters squared, and we find out that the Keck telescope is capable of 400 times the light gathering power than a half of a meter telescope. A large difference. Much greater than just a multiplication because of that squared value. All right, let's get to the next problem. In the resolving power calculations, here's our first example, which is number 8. We have the arc seconds is equal to 13.8 arc seconds over the diameter of the telescope in centimeters. And so we take a 25 centimeter telescope, we take 13.8, we divide by the 25 centimeters, and we find out that that telescope has a resolving power of about 0.552 arc seconds. Finally, the last type of power of a telescope is the magnifying power. And we take the focal length of a telescope divided by the focal length of the eyepiece. And in this case, we're using our Manheim Township Astronomy Meade LX10, which is our Schmidt-Cassegrain type of telescope. It has a diameter of 203.2 millimeters, which for this problem is not needed. But it does have this information, a objective mirror focal length of 2,000 millimeters. That is required. That's the FO here. And we're using a 35 millimeter eyepiece, and that's FE. So we're solving for what is the magnification in X. So we take 2,000 millimeters, we divide by 35 millimeters, make sure the units are the same for both of these, and we find out that approximately 57 times magnification is the result here. So hopefully this helped. If you have any questions, please talk to me in class. Thanks a lot. Have a great day.